Okay, slightly different style of video this one. Instead of teaching something, I'm going to be going over a rather hard differentiation paper. It's one that I made, so you won't be finding the questions elsewhere. It won't be a past paper that you've done, mainly because I don't want to be sued by Edexcel, but it is relevant for, well, at this point, all of A-level differentiation. And, you know, anything equivalent, pre-university differentiation, Calc 1, it's called in the States, I believe, something like that. Now, just to preface this, if you are an A-level student, this is not a comprehensive paper with everything possible. Notably, it is missing parametric differentiation, implicit differentiation, and rates of change, okay? So if those three things are things you need to work on, they won't be included here. Sorry, haven't done the videos on them yet. They will be coming eventually. But this paper, it's 4 questions, rather difficult and also standard kind of exam questions. So let's start off because I don't know how long this is going to go on for. And starting off, we are asked to prove from first principles that the derivative of sine x is cos x. Just going to check we're still recording. We are. Okay. Now, reason I've included this, yes, I've got a video on it, but it is a very, very common exam question. Didn't invent this one, unfortunately. The rest I did though. So, let's prove it, shall we? The derivative of sine x is cos x from first principles. If we're working with first principles, then we are working with the equation f of x minus h minus f of x divided by h. And that, of course, is in the limit as h tends to 0. So, let's put our sine of x into here. And again, some people do struggle with this, so let's see how we do that. So I'm going to keep my limit as h tends to 0 there. Always want to keep that there until I've finished because that is the correct notation. And my f of x minus h means this argument within sine, this x, is changing to x minus h minus f of x, which is sine of x, all divided by h. Now, at this point, I'm going to want to use my addition formula. So if we remember, sine A minus B is equal to sine A cos B plus cos A sine B. So if I use that logic, but using x and h as my A and B, I'll keep the colours consistent, sorry, then I end up with that I have got sine x cos h, not cosh. Always think that's cosh. If you don't know what cosh is yet, don't worry about it. Plus sine h cos x minus sine of x, all divided by h. Okay. Now, at this point, we need to do a bit of a weird manipulation, and we need to use a bit of a weird approximation as well. What I'm going to do is I'm almost going to split this fraction. In fact, I'm going to move it around because I can do that on here. I'm going to split this fraction and I'm going to move it around like this first of all. Ooh, should have moved the plus with it. There we go. I'm just going to move it around. I can do that. I can reorder things however I want. I'm the boss. So I've got sine x cos h minus sine x plus sine h cos x. And I'm essentially going to split this down the middle. Okay. And I'm going to turn this into 2 fractions, keeping my limit in there. I'm going to start with sine x cos h minus sine of x on the top here, and I'm just going to factor out my sine of x. So I get sine x cos h minus 1, and I'm adding to that sine h, not sinh, cos x over h. The reason I'm doing this is because here, this cos h minus 1 over h, and here, this sine h over h have approximations. If you're doing A-level in the UK, then you will be given these approximations in the exam, okay? If not, go back, watch my video on them. I do go into these approximations in detail. But if you're in the UK doing A-level, you will be given them. Those approximations are that cos h minus 1 divided by h, as h tends to 0, is 0, okay? And sine h over h, as h tends to 0, is 1. And this leaves us with, that's my limit taken care of. Well, this thing disappears because it's multiplied by 0. This thing becomes 1, and I just end up with cos of x. And that is how I prove cos from first principles of sine. Again, if you want to get a bit more information on those approximations, check out my video entitled Differentiating Sine and Cos. Not that hard to find. Right then, let's move on to something a bit juicier. So, find f prime of x of the following. And although I didn't write it explicitly, it is of course implied that each of these is an f of x. So let's start off with cot of 4x. Now, the derivative of cot, I have proven in another video. I need to stop plugging. I'm not going to plug. Apart from subscribe, that's a good plug. Do that one. But I'll stop plugging other videos. The derivative of cot is a standard result. The derivative of cot, so d by dx of cot of x is minus cosec squared of x. Okay? That is a standard trig result. Proof of which you can do either by the quotient rule or by the chain rule. So, but here I've got a 4. And hopefully by now we know with the chain rule or just with trig functions in general, if I'm differentiating and I've got a 4 in here, well, that 4 is going to want to be brought outside. And we end up with that the derivative of cot of 4x is minus 4 cosec squared of 4x. Just a nice simple application of the chain rule. Just saying that whatever is inside this bracket here needs to be differentiated, which is I'm not drawing, oops. Whatever is inside this bracket here needs to be differentiated and brought outside. So the derivative of 4x is just 4, so we bring that outside and we leave the interior. And we just end up with minus 4 cosec squared 4x. Right, next one, e to the 3x arc cos of 2x. Okay, a lot going on here, but what we should notice is that we have a function multiplied by another function. We have a product of two functions, we have a product rule. So as a reminder, do this one in blue just so we don't get mixed up with up top. The product rule, if we want to find the derivative of f of x times by g of x, it turns into f of x times g prime of x plus f prime of x g of x. And I will just move that kind of up and out of the way. Ooh. And get rid of that because that's not necessary. First time recording on an iPad. Let's see how we go. Yeah, there we go. So that's my product rule. So I need to assign each of these a function. So let's call e to the 3x f of x and arc cos 2x g of x. So in which case, let's then find f prime of x. Well, e to the 3x, nice and easy to differentiate. We're going to use the chain rule and we're going to say that we have e to the 3x. So the chain rule says that we need to take whatever is inside the function, which is 3x, differentiate it, which is 3, and bring it down in front. Nice simple rules for differentiating e's. So my f prime of x is 3e to the 3x. Now let's do g prime of x. So g prime of x can be slightly trickier. We're going to need to use our standard result for the derivative of arc cos. So again, I've proved that in a previous video. I need to stop plugging things, but the derivative of arc cos d dx of arc cos, and I've just realized there's a lovely spelling error in that question. If anyone's already commented to yell at me for that, then go for it. But I still believe arc cos should only have one c, so, you know, I think that was just my brain acting out. Anyway, the derivative of arc cos is minus 1 over the square root of 1 minus x squared. There's a standard result that we should know from trig. We can prove it using a funny little method of some weird substitutions. But this is an arc cos of 2 of x. So we're going to need to treat this like a chain rule. And it's the same as any other chain rule, whereby we take the derivative of that 2x, although I'm starting to hide it now. We take the derivative of that 2x, which is 2, we bring it outside, so there, of our final result, and then we make sure to include it in our x. Making sure to remember that it's the entire argument there squared. So we end up with minus 2 over the square root of 1 minus 4x squared. And that is my results for g prime of x. Now I'm just going to get rid of this. And now we can put the whole thing together and we can say that, well, f of x is e to the 3x, g prime of x is minus 2 over the square root of 1 minus 4x squared. And then we're going to add to that f prime of x, which is 3e to the 3x, times g of x, which is r cos, spelled correctly, times 2x. There's some simplifications you can do. You know, if you want to bring the e to the 3x out, that's fine. But I think I'm happy with how that is. It looks awful. It looks deranged as intended. Okay. Last one then. The square root of 2x squared plus 3 times ln of sine x. So there's a lot going on with this one. First of all, first thing to notice is I've got a function times by another function. Always be aware, this is not 3 functions times by together. It is not 2x squared plus 3 rooted times ln times sine x. The ln and the sine x are partnered up. The sine x is inside the ln. Yeah, the sine x is inside the function of ln. So it is a product rule, with that being my f of x and that being my g of x. So let's apply the product rule and see how that goes. So let's go with f prime of x. Well, I'm going to need to use the chain rule. So let me make a little space over here to do that and say that f of x is, and it's a square root, so I'm going to want to change it into a power of a half because it'll make things easier. And then let's apply the chain rule. The chain rule in general, we take the derivative of the interior. So the derivative of 2x squared plus 3 is just 4x. And then we put it outside the total thing differentiated, meaning we want to take that 1/2, bring it down in front, and then reduce that power by a half. So I end up with 4x over 2 times 2x squared plus 3 to the minus a half. Okay? Chain rule, if you want to write it out as 2x squared plus 3 equals u, and then do dy by du and dx by du separately, that's fine. But this is just a nice, quick and easy way of doing things. Am I losing my voice already? It is the middle of the night. That might be why. So just to simplify things down a bit, that 4x over 2 becomes 2x, and then we end up with 2x cubed plus 3 to the power of minus a half. Of course, I could do that as a denominator square rooted, but I'm not going to worry about that. I can just keep it like this. Right, now we need to find g prime of x. Well, this is going to be a bit annoying because we've got ln of sine x. Once again, I'm going to use the chain rule. But I'm going to use the chain rule a little bit more directly this time, just to make sure the point gets fully across. So let's put sine of x equals u. And then say that du by dx, well, sine differentiates to cos of x. And then I want to find dy du. And y here is just going to equal ln of u, and the derivative of ln, or any log, is just 1 over u. Multiply those together, and I end up with, so multiply these two together as per the chain rule, I end up with cos of x divided by u, which is sine of x. And that cos over sine, or cot, which is quite nice. I just end up with a cot of x. Okay, so my g prime of x is simply cot x. Now, I'm going to get away with leaving some of this, but yeah. Now we can put it all together using our product rule from earlier. That's still at the top of the screen there. So we end up with f of x which is root 2x squared plus 3 times g prime of x, which is cot of x, plus f prime of x, which is 2x cubed plus 3 to the minus a half times by g of x, which is ln of sine x. Ooh, quite a mouthful. But again, no one said the answers are going to be pretty. Right then, let's move on. Question 3. Find the tangent to the curve 2x plus 1 over 5x squared plus 1 at its y-intercept. Now this is immediately throwing me a lifeline. Hence, find where this tangent intersects this graph. So, a couple of things that I want to identify immediately. The word tangent immediately means I'm going to be working with the same gradient. So if I find the gradient of this curve at this point, I'm going to be able to find the gradient of my tangent. Second thing that's helpful, as I alluded to, is the fact it says y-intercept. That'll make things a lot simpler down the line because hopefully we know that the coordinates of the y-intercept are going to have an x value of 0. And whenever we see an x value of 0, we're having a good time. So first of all, I'm going to just kind of delete some of this mess, and I'm going to say that y is 2x plus 1 over 5x squared plus 1. And from here, I think the easiest thing to do first of all is let's just find this y-intercept. Let's get these coordinates done out the way. I know that my x value is going to be 0, so if I put 0 into this equation, I'll get 2 times 0 is 0 plus 1 over 5 times 0 squared is 0 plus 1, and I get 1. So immediately, I'm happy. I know the coordinates on the graph that I'm working with are at 0 and 1. Beautiful, no weird numbers, hopefully. Okay, so I've got this now, and what I want to do is start differentiating. I need to get the gradients to be able to form an equation for my tangent. So let's differentiate 2x plus 1 over 5x squared plus 1. Well, this is just the quotient rule. It is a fraction. 2x squared plus 1 divided by 5x squared plus 1. F of x over g of x. So I've got f of x as 2x plus 1 and g of x as 5x squared plus 1. Now my quotient rule tells me that this differential, and I'm going to say the thing I say every time so that we can remember it, is g of x is on the bottom here, so it is going to be on the bottom here, but it's squared. And because he's been on the bottom all the time, he gets to go first. So we get g of x times f prime of x minus f of x g prime of x. And that's the equation I'm going to be working with. So let's finish this off and find f prime of x. Well, that's just going to be 2. And g prime of x is going to be 2 times the 5 is 10, x to the power of 1. So just 10x. Nice and easy, just some simple polynomials after all that rubbish we had earlier with trigs. Right, now let's combine these together. So g of x is 5x squared plus 1 times f prime of x is 2 minus f prime of x is 2x plus 1 times g prime of x is 10x all over 5x squared plus 1 all squared. Okay, now let's just do some, I'll keep the question up at the top. Let's just do some simplification here. So I'll expand out that into 10x squared plus 2, and I'll expand this out into minus 2x times 10x is 20x squared. 1 times 10x is 10x, so minus 10x over, and I think I'm probably safe to assume I don't need to expand out the bottom. Sometimes I may do, but in this case, just looking at the vibe of the equation, I don't think I do. And then let's just simplify the top a little bit. What can I do here? Well, I can say that is minus 10x squared minus, nope, not minus 20x, minus 10x plus 2. And that is my gradient of this curve, my derivative. So now I want to switch my attention to the tangent. So my tangent passes through the point 0, 1, as we know, which means I need to find the gradient of the tangent at the x-coordinate 0. So let's pop 0 into my equation for gradient. Well, what do I get? I get 0 minus 0 plus 2 divided by 0 plus 1 squared. 1 squared is 1. I get 2 divided by 1. My gradient is 2. Very nice. So I get y equals 2x plus c, because my tangent is going to be a straight line, so it's going to be y equals mx plus c. Okay then, so now how do we find c? Well, the keen eyes amongst you might notice that we know our tangent passes through the point 0, 1, meaning it is going to have a y-intercept by default of 1. So c is going to be 1. Of course, we could very quickly prove that by putting these coordinates into here and seeing 1 equals 2 times 0 plus c, and c is 1. So the equation for my tangent is y equals 2x plus 1. However, there's another part to this question. It says, hence, find where this tangent intersects this graph. Now, a lot of my students stop at this point in the working and they say, I'm finished, because it only intersects this graph at this one point. However, the reason this is a question is, imagine I have a graph that looks like this, and I have a tangent to this point here. Yes, it intersects the graph here, but it has a second intersection point, meaning I need to go looking just in case my graph has one. And spoiler alert, it does. So if I want to find an intersection, I need to equate my graphs together. So I need to equate 2x plus 1 to 2x plus 1 over 5x squared plus 1. Now I need to solve for x. Now, some of you might have a thought here, which is, and I'm going to zoom in for dramatic effect, because some of you might have a thought, which is, hang on, 2x plus 1 cancel, multiply both sides by the 5x plus 1 equals 1, minus 1 from both sides, 5x squared equals 0, x equals 0. There's no other intersection points apart from the one that I already know, which is x is equal to 0. And some of you, and I know who you are, might get to this point and say, okay, I am done. Perfecto, finished. But there is something hiding away. Let's see what happens if I just multiply both sides by 5x squared plus 1. So 2x plus 1 times 5x squared plus 1 equals 2x plus 1. Ooh, just cancel. No, don't cancel. Because let's see what happens if we don't. Well, that's going to become 10x cubed plus 5x squared plus 1 plus 2x equals 2x plus 1. And then, well, I can minus a 2x from both sides, minus a 1 from both sides, and I just end up with 10x cubed plus 5x squared equals 0. Minus the 5x squared from both sides, and I get 10x cubed equals minus 5x squared. This isn't starting to look like 0. I mean, yeah, one of the options here would be that x equals 0, but what's going to happen if I cancel an x squared? Well, if I cancel an x squared, I get 10x equals minus 5. And hence, x is also equal to minus a half. And if you put this into a calculator or a graphing system, Desmos or likewise, then you will actually notice that there are 2 points of intersection. One is the one we already knew about, the y-intercept at 0, 1. But one is also when x is minus a half. And if we just want to get that y-coordinate, by the way, y equals 2 times minus a half plus 1. 2 times minus a half is minus 1 plus 1 is 0. So actually, my other option is the x-intercept at minus a half 0. So just a quick word on why on earth is this happening? Why can I not just cancel the 2x plus 1 immediately? Well, I'm going to relate this to trig, as all amazing things are usually related to trig. When you're solving a trig equation, you might have noticed that if you try and cancel out a sine or a cos on either side of the equation, you end up missing values. And this is because whenever you delete, you divide both sides by the same thing, you're basically ignoring the fact that they're possible. What's truly happening here is, yes, we have an equation that looks like we can just cancel, but graphically, there are solutions that you're hiding away by doing so. And it's true for trig equations, and it's true for these as well. So if you're ever cancelling equations, then you always need to consider the fact that they are also valid. By that I mean, consider the fact that 2x plus 1 is also a solution. If 2x plus 1 is also a solution, 2x plus 1 is equal to 0, and if I can rearrange this and once again get that x is equal to minus a half. This is something tough to see. Lots and lots of lost marks on this one. But if you notice this and you never just cancel terms willy-nilly, you always consider where they are, then you'll be fine. One last thing I want to mention is, oh, didn't you just cancel here, 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 and here? No, I minus them, okay? Cancellation from a minus is slightly different than dividing both sides by the same thing, which is why it was acceptable here and I still got to my solutions. Okay, last question, split into an A and a B, is a bit of modeling. And it's a very common question. Again, so I didn't really make this one up myself. It's a very, very common idea of a question, which is relating the surface area and the volume of a system. So let's start off with part A here. A cylinder has a radius of r and a height of h, and it has a surface area of 500 meters squared. So it's a massive cylinder. Now, oh, caught me through. Surface area of the cylinder is 500. We don't know any information about the dimensions, so let's just write it out algebraically. So let's say 500 is equal to, well, what's the surface area of a cylinder? Well, just a very quick proof with my amazing drawing skills. Surface area of a cylinder is going to be the area of the top plus the area of the bottom. They're both going to be equal circles that are both going to be pi r squared. So 2 lots of pi r squared. There's my radius. Plus the surface area of this curved edge. Now, what on earth is the surface area of a curved edge of a cylinder? Well, a curved edge of a cylinder is essentially just a rectangle. Don't know why I'm drawing it out with my hands. It is a rectangle that has been wrapped around itself. That rectangle has a height of h, and it has a base of the circumference of the bottom of the cylinder. Try and visualize that. Circumference is 2 pi r, so this surface area here is 2 pi rh. Okay, I'm going to just kind of delete little bits of working as I go because I don't have much room. My handwriting is not great to be able to use less room. So here's my surface area. Now, what do I need? Well, I need an expression for my volume. And volume, as we should probably know, is equal to the surface area of one of the faces times by the height. So pi r squared times by h. Now, what I need to do is I need to try and relate these two equations together a little bit. Let's have a look what I've got up here. Well, I've got an expression for pi r squared, but I'm not happy with the way that's looking, mainly because I want to try and get rid of h. Now, most questions that pose this give you the answer and tell you to work towards it. The reason I haven't done that is because I want to illustrate why we're getting rid of h. The reason we're getting rid of h is because at some point I'm going to want to consider a differential equation using volume and radius. Why not h? Well, in general, when we're working with cylinders, it's typically the radius that changes. If we're opening something, etc., it's typically the radius that changes. So I could rearrange for pi r squared and get a nice expression in h, but that's going to have too many variables. I'm going to have a v, an r, and a h. Not a fan. I'd rather just keep it with as little variables as possible and get rid of the h. So let's rearrange this top equation for h. So let's do 500 minus 2 pi r squared is equal to 2 pi r h. And now just divide each side by that 2 pi r. And that is going to equal h. Now my volume is equal to pi r squared times h. So if I multiply this entire thing by my pi r squared, I should get my volume. Now let's see, are there any cancellations I can do here? Well, that r can cancel with one of those, that pi can cancel with one of those, and I can definitely divide that by 2. So in fact, it cancels down quite nicely. If I divide this numerator here by 2, I get 250 minus pi r squared equals v, multiply that r in, and I get 250r minus pi r cubed is equal to v. And I'm going to bring that down with me because I'm going to need it for this brutal last question here, which is calculate the maximum value for this volume and justify it is a maximum. So whenever you see the word maximum, there should be one thought in your mind, and that thought is stationary points, okay? When we're dealing with maximums of graphs, minimums of graphs, it is a stationary point, and Keeley, our gradient must be 0. Are we still recording? Yes. Are we still recording on the camera? Yes. Okay. Just checking, because I'm not having another incident with having to re-record an entire thing, because these take ages and it is very late. Okay. So where were we? Stationary points, dy dx is going to equal 0. But I don't have a y or an x. I have a v, and that's equal to 250r minus pi r cubed. But what we need to notice here is that I kind of do have a y and an x. I have a variable that is equal to a function containing only one other variable. Pi is not a variable, it's a constant. Don't get confused because it's a letter, because sometimes I do even when I see a pi. I think, oh, what, what's going on here? Is it another variable? No, that'd be psychotic. So I essentially have a y is equal to 250x minus pi x cubed. So instead of doing dy by dx, let's do dv by dr. And this will be a nice differential. I'll end up with 250 minus 3 pi r squared. Now, I know I'm going to want to equate that to 0. So if I rearrange, I get 3 pi r squared is equal to 250. Again, it's 0 because the gradient at a maximum, at a stationary point, is going to be 0. And now I can do some horrible looking maths here, and I can rearrange for r. And if you're sat there with a calculator, which I hope you are, I will let you find r here. But if you do that, I believe, unless my earlier calculations were incorrect, that you should get a value of 858. .15. If there was a weird cut there, it's because I said the wrong numbers, because it's late and I can't count to 10. So we have our r as that. That is the radius at the maximum point. So what's actually happening here is, as I kind of described earlier, we have a cylinder that's attached to a large structure, and that cylinder is slowly opening, right? Think of it as like a a tap maybe, slowly opening and letting something out, which is increasing or decreasing the volume of the cylinder. Now, if my maximum value is at R equals 5.15, I'm asked to find the maximum value for the volume, so I need to put that back into my original equation. So 250 times 5.15 minus pi 5.15 cubed is going to equal V, and my sources tell me that that is then going to be equal to 858 meters cubed. We have got a massive cylinder that we are dealing with. Okay then, so that's our maximum value of volume, but we are asked to justify that it is a maximum. Two ways to do this. I'm going to use the posh way, see my video on the posh way to find it, and let's see if that works. That posh way involves a second derivative. So what's my second derivative? Well, my first derivative is up here, and that's going to be quite nice to differentiate because my 250 is going to disappear. My 2 is going to be brought down, so I get minus 6 times pi r. Now I need to put my radius of 5.15 into here, at which point I can already tell I'm going to get a negative number. I believe you get negative 97, but without even knowing that exact value, I can tell I've got a positive times a positive times a positive times a negative. It's going to be negative. It is negative, hence maximum. Yeah, remember when we have a negative second derivative, we end up with a maximum point. Okay, that is it for all of those. This is a bit more of a different video. If anyone has watched to the end, thank you very much. And I'll probably be doing one of these each time we get to the end of a pretty tricky subject.